Okay, welcome back. This is 9.7, should be 9.7. And we're talking about Pascal's Triangle and the Binomial Theorem. Okay, so here we go. Um, oops. Okay, so Pascal's Triangle, if you've not seen it, looks like one of these. So down the sides there's ones, and then what you're doing is kind of adding these two top guys together to get the one below it. So there's a 1 on the sides, and then 1 plus 2 is 3, and then again 1 plus 2 is 3. And there's all kinds of cool properties of this triangle. We'll be using it with the binomial theorem, so it'll give us coefficients on expanded products of binomials, right? So you'll be able to do cool things like if you have, I don't know, x plus 1 to the third, you can kind of expand it pretty quickly instead of having to do all the FOIL stuff. So x cubed plus 3x squared plus 3x plus 1. Okay? And you can kind of see the 1, 3, 3, 1 is over here. So there's a connection between that triangle and these expansions. Okay, so we'll play around with those kind of issues in this section. There's some proofy stuff here too. We also want to make sure that we recall how to evaluate this NCR notation. So evaluate NCR, and that's just the n factorial all over r factorial times n minus r. Okay, factorial. Right. There's two types of proofs when you're dealing with these kind of questions. There's kind of an algebraic type proof, and then a combinatorial type proof. Let's just look quickly at a algebraic type, and I'll show you a combinatorial later. They don't really do combinatorial proofs in the homework, as far as I know, but I'll show you one anyways. So, anyways. An algebraic type, number 5, we want to show this combinatorial identity that n choose r is equal to n choose n minus r. Okay. And what you do, and we're not even going to write it like a direct proof, we're just going to show it like a kind of like a trigonometric identity, right? So you're going to start on one side, go to the other, and use the definitions. So starting on the left hand side, we note that n choose r is equal to n factorial all over r factorial times n minus r factorial. It's just the definition. We could use the commutative property of multiplication in the denominator to rewrite that as n minus r factorial times r factorial. And then we can use just basic rules of arithmetic to rewrite r factorial as kind of a difference, right? So let's rewrite it as how do I want to rewrite this? N minus n plus, yeah, that'll do it, r factorial. And so you see that's equivalent to r factorial because n minus n is just 0. Okay, so 0 plus r is r, and that's r factorial, and that's just the exact same expression. This is the exact same thing as this, right? Okay, then I can rewrite that using distributive laws. So I have n factorial all over n minus r factorial times n minus r factorial. And then you could use the definition of this NCR notation to just rewrite that as n choose n minus r. Okay, so that shows which is the other side. So which is the right hand side, which is what I was trying to show. All right. So no real big issue there. Let's move on to Pascal's triangle. And when we work with Pascal's triangle, what we're going to do, if you look back up to the top, we're not really going to work with it as a triangle. What we're going to do is kind of push all of the terms to the side, and it'll be like a right triangle at the end. Okay, so this is section 2 in my notes. Pascal's triangle, or Pascal's formula in particular, we want from the triangle. Okay, so that relationship I described up here, where the two above it add together to give you the one below it. So 1 plus 2 gives you the 3, and then 3 plus the 3 give you the 6 here. That relationship can be expressed using that NCR notation. Okay, so that's what we're after, and we're going to do a little table here to express that. And on down this column, I'm going to put n, and along the row I'm going to put r. So I have 0, 1, 2, 3. I need to go up to 4. And on the row I have 0, 1, 2, 3, and then up to 4. And then I'm going to put Pascal's triangle in here. Okay, but I'm going to smush it against the wall. Okay, so that'd be that. And then this one is 2, 1. And then this one is 3, 3, 1. And then this one is 4, 6, 4, 1. Okay. Okay, so one of the cool things is these numbers in the chart are the result of just going NCR, right? So this 3 right here is the result of doing 3 choose 1. Okay, so if you look at that thing, 3 choose 1, it's 3 factorial over 1 factorial times 3 minus 1 factorial, which of course is 3 factorial all over 2 factorial, which turns out to just be 3. Okay, so you can also then get all of these numbers from Pascal's triangle, not just by doing the sort of, ones along the side and then add up the top to get to the bottom. You can use NCR formula in order to produce all these numbers with this chart. Okay, and then the other sort of the fact that the two things above equal the thing below, and this format, it looks like this: the 3 plus the 3 equals 6, the 1 plus the 2 equals the 3. We want to write that in NCR notation. Okay, so how do I do that? It's going to be, for instance, for that first red box I drew, the circled 3 is 3 choose 1. The 3 next to it, which I just am circling now, is 3 choose 2, and then that of course equals 4 choose 3. Okay, so we want to rewrite that into a general form, and in general, that's Pascal's formula, okay, that we're introducing here. So in general, we have n plus 1 choose r equal to n choose r minus 1, and then plus n choose r. Okay, so the n choose r was this one, and the n choose r minus 1 was that one. Okay, we want to prove this, and this time we'll do more of the combinatorial type proof rather than the algebraic. Okay, just to give you a flavor of how that goes. Okay, so combinatorial type. And this is more of a reasoning proof. So we'll start by kind of invoking the set of n+1 elements. So suppose S is the set of elements, let's say x1, x2, x3, all the way up to x sub n, and then x sub n plus 1. Okay. Then consider subsets of this set. And we consider subsets of size R of S. Okay, so to count up the number of subsets of a set, you're doing the NCR, right? So if you have n elements in a set, the number of subsets of size R is n choose R. Okay. All right. Here we're working with a set with n+1 elements in it. So maybe that looks a little scribbly. X sub n plus 1. And that's kind of what this thing at the top of the page on the left here that I'm putting in a box. That's kind of what this thing is saying. This thing is counting the number of elements, number of subsets rather, of size R taken from a set with n+1 elements. Okay, so the way we're going to kind of analyze it is by cutting it into two disjoint sets of subsets. Okay, so one set of subsets is the case where x sub n plus 1 is included in the subset. So the truth is, either when you're creating these subsets, either x sub n plus 1 will be in the subset or it won't. Okay, I think everybody can agree to that, right? So we look at each case. So let's say case 1, let x sub n plus 1 be in the subset. And we want to count how many of these subsets there are. Okay, so if we know x sub n plus 1 is in the subset, we're kind of just choosing n out from n elements. Okay, so we're basically dealing with a set of size n. So like the set x sub 1, x sub 2, all the way up to x sub n. And then we're choosing r minus 1 elements from it. Okay, so it's like we have this set that I just put in parentheses, and we want to choose r minus 1 elements from it, because we already chose one of them, right? Okay, so supposing x sub n plus 1 is in this subset, we need to choose then r minus 1 from or r minus 1 elements from the remaining n elements. For the remainder of our subset. And then this can be done in how many ways? Well, that's n choose r minus 1. Okay, this can be done in n choose r minus 1 ways. Okay. So the number of subsets that contain x sub n plus 1 is n choose r minus 1. And then there's case 2. where x sub n plus 1 is not in the subset. So say x sub n plus 1 is not in the subset. Okay, so in that case, it's almost exactly the same as this case. We've kind of removed x sub n plus 1 from the set, so we only have n elements left to choose from. And now, because we're not including x sub n plus 1, there's actually r elements to choose. Okay, so now we have, or maybe I should just write it in the proof, right? So say x sub n plus 1 is not in the subset. Now we have n elements to choose from. And we need to choose r of them. Okay, so how many ways can you do that? That's n choose r. Okay, so the number of subsets that contain x sub n plus 1 is n choose r minus 1, and then the number of subsets that don't contain x sub n plus 1 is n choose r. So hence the total number of subsets of an n plus 1 element sets where the subset has size r is, okay, so on one side we have, this n plus 1 choose r, and so the number of subsets that have x sub n plus 1 in it would be n choose r minus 1, and then the ones that have x sub n plus 1 not in it will be n choose r. Okay, and that's just Pascal's formula. Okay, so a little bit more involved. I don't like these kind of combinatorial proofs. They're always kind of fishy, and it's kind of like, did I really cover all my bases? And sometimes they're a nightmare just to come up with, right? So where do I even start, I don't know. That's where the programming comes in. How could I program a computer to do this? I could barely kind of pull it out of my guts, on my own. How am I going to get a computer to do it on its own? So, I keep that in mind. That's one of the things that used to drive me about proofs and computers, right? Trying to figure out, maybe if I could program a computer to do this, maybe I can independently figure out how to do it on my own, and vice versa. I don't know. Anyways, I guess that's neither here nor there anymore. Let's just move on to the binomial theorem. Okay. Binomial theorem. So note this a plus b cubed. Okay. You can expand it and write a plus b times a plus b times a plus b, and then you could FOIL it out, so a times a, and let's not go a squared, let's write a times a. Okay, so a times a plus a times b plus b times a plus b times b, and then we have to multiply that by a plus b. And then, so a times a times a is a times a times a, right? So now I'm just kind of doing distribution. And then this A times B times A. And then this, right, B times A plus B times B times B. And then you have to do it again, but with the second term, plus A times B plus A times B times B plus B times A times B plus, whoops, so I screwed one up there above it. This should be B times A. And then plus B times B times B. Okay, so how does all this connect to probability and counting problems? Well, if you look at what you have here, these individual terms, these are just all of the different ways of writing a three elements with A's and B's, right? So in the first slot, you can either choose A or B. In the second slot, you can either choose A or B. And then the third slot, you can either choose A or B, right? And it's the multiplication rule that will tell you then the number of terms is 8, right? So there's, you should have an A, you should have an A, B, and all of those different permutations, right? And do we have that, right? So there's 1, 2, 3, 4, 5, 6, 7, 8. Yeah. And you'll see all the different orderings are there. A, ABA, BAA, all that stuff that's in this tree right here to the left is contained in all of these elements. So what's the deal here? It's basically it's a listing of all of these different I don't know, permutations. Yeah, it's just the listing of ABA. So hopefully you can appreciate it's kind of a probability, permutation type problem. Okay, and other ways you can think of it, it's like, okay, I'm going to take either in this binomial either take A or B, so I'll take A. In this binomial either take A or B, so maybe B. In this binomial take A or B, I'll take B. And what you have at the result in the end down here is just the listing of all possible combinations. Okay. So ordering matters, and ordering matters, but repetition is allowed. So if you think about that chart of different kinds of mechanisms we use to determine the number of things, it's not exactly permutation, right? The order is important, but we have some repetition. So it's more along the lines of when we were asked to find the number of orderings of something like the word bin, right? So how would I find the number of different orderings of the word bin? Well, there's 4 letters, so 4 factorial all over the number of repeats. So there's 2 E's, 1 B, and then 1 N. In our case, what we want to do, I think I'm bumbling this a bit, but what we want to do is find the number of we want to find the coefficients. Okay, sorry. So at this point, what I'm doing is I'm not finding that number 8. I already know how many there are. The problem is finding how many repeats there are, because I want to ultimately, when you write out your expression, you don't write it out like this. You combine the like terms. So we have a cubed plus, how many AABs are there? There's 1. Let me put it in a different color. There's 1, 2, 3. There's 3 of them. Okay, so I need to know that there's 3 a squared b's. And then how many of the b squared a's are there? If you go through and count, there's 1, to 3 of those. Okay, so 3 b squared a's, and then plus the b cubes. Okay, so my problem right now that I'm kind of moved on to without telling you is not the issue of finding out how many, that there were 8 of these things. No, the issue now becomes the coefficients. Okay. So how do I figure out those coefficients? And what I'm getting at, it's the same problem as this problem here, where you're trying to order the letters of a word with repeated letters. Okay. So in particular, in our case, for example, the second term here with AABs, you're just figuring out the number of ways to order the word AAB. And what is that? Well, that's 3 factorial all over 2 factorial. And because we only have 2 letters to deal with, 2 different letters, it'll be 2 factorial times 3 minus the 2 factorial. Okay, and you could probably see what that is. That's an NCR right there. That's 3 choose 2. Okay, so it turns out that these coefficients are just these NCR things. Okay, and in particular, those coefficients turn out then to be the numbers from Pascal's Triangle, where I started back here, right? So you could rewrite x plus 1 cubed as 3 choose 0 times x cubed plus 3 choose 1 times x squared plus 3 choose 2 times x plus 3 choose 3 times 1. Okay. Okay, so it's weirdly combinatorial, and in a way that's probably kind of unexpected for most students. Anyways, let me give you the general formula now that I've kind of butchered that to death. Hopefully you're not too confused at this point, but in general, at least if nothing else, you can appreciate the fact that this has, when you expand these, there's an underlying kind of combinatorial structure to it. Okay, so in general, to expand a plus b to the n, what you're going to do is use the summation formula. K equals 0 to n of n choose k times a to the n minus k times b to the k. All right, so you can see the exponents on all these terms. You start with a cubed, and then the exponent goes down by 1 each time. Okay, so this last one would just be a to the 0. So it goes a cubed, a squared, a, and then a to the 0, a to the 1, then a to the 0. On the other hand, the b terms are all going up, right? So we kind of start with a b to the 0. Let me put that maybe in a different color. And then it goes b to the 1, and then it goes b to the 2, and then it goes b to the 3, right? So it's b to the 0, b to the 1, b to the 2, b to the 3. Okay, and that's what those funny exponents are doing for you right here. Okay, so we're starting with a to the n minus 0 and b to the 0, and then k goes from 0 to n. Okay. Let's from this formula you get some really neat properties. So, for instance, note, I guess, what happens when you have the sum from k equals 0 to n of n choose k, and your a and b's are both 1s. So you have 1 to the n minus k times 1 to the k. All right. In this case, 1 to any power is just 1. So you end up with a sum from k equals 0 to n of n choose k, which you could write out if you want as n choose 0 plus n choose 1 plus n choose 2 plus all the way up to n choose n. Okay, and what we're saying from the binomial theorem is that a plus b to the n is equal to this thing. So what was a and what was b? Well, a was 1. Okay, so we have 1 plus, and then b was 1. And then we're raising it to the n, right? So the weird thing is this thing equals 2 to the n. And if you look at what the sum is really just a row of Pascal's triangle. So if you rip back to Pascal's triangle, maybe I should rewrite another one. Okay, let me rewrite one really quick. If you look at the sum of the rows of Pascal's triangle, there'll always be powers of 2. So the first row 1 is 2 to the 0. The second row, if you add them, so we're talking about adding them all, is 2, which is 2 to the 1. And then if I add these, 1 plus 2 plus 1 is 4, which is 2 squared. 1 plus 3 plus 3 plus 1 is 8, which is 2 cubed. 1 plus 4 plus 6 plus 4 plus 1. So we have 10 plus 5 plus 1, 16, 2 to the 4th. So this should be 2 to the 5th, right? This should be 32. Let's make sure. 1 plus 5 is 6, plus 10 is 16, plus 10 is 26, plus 5 is 31, plus 2, or plus 1 is 30. Awesome. Ain't that really neat? Okay, so you get all kinds of extra little cool patterns popping out. Let's see what WebAssign has for us with regards to problems. So sometimes they'll just want you to expand products and find the resulting polynomials. So u minus 3v to the 4th. Okay. Be a little careful. This is really the same as u plus negative 3v to the 4th. And then what we need to do is just plop it into our formula. So it'll be u to the 4th plus, if you go to the 4th row of Pascal's triangle, we're going to need to use, it's actually, if you start here as 0, 1, 2, 3, 4, we need these coefficients. Okay, so the first one I have a 1 on it, plus 4 times, now we decrease the exponent on u, but increase the exponent on negative 3v. Okay. And then we have 6 as our coefficient, decrease the exponent on u, increase the exponent on v, negative 3v, sorry. And then plus, we have 4 times decrease the exponent on u, increase the exponent on negative 3v, and then plus 1 times decrease the exponent on u, so that would just be u to the 0, which is 1, and increase the exponent on negative 3v. So we'll have 4. And they probably want you to simplify this. So negative 3 times 4, oops, probably want a negative in there. It was negative 12 u cubed v. Negative 3 squared is 9, times 6 is 54. We have u squared v squared. Minus 27 times 4 is 54. uv cubed. And then plus 81. Whoops, this should be 108, not 54. Sorry. Wait. And then finally 81 v to the 4th. Okay, so they'll come up with some weird problems for you. Finding coefficients on expanded. Find the coefficient on x to the 7 in the expansion of 3x plus 2 to the 10th. So clearly you don't want to expand that whole thing. That would be kind of a nightmare, even using the binomial theorem here. But what you're going to do is kind of remind yourself, okay, the binomial theorem is k equals 0 to n of n choose k times a to the n minus k times b to the k. And then you want to figure out the exponent on, I want the exponent on the x to be 7, okay? So you could even write this out with these two a and b filled in, right? So this would be k equals 0 to n of n choose k. We have 3x to the n minus k, and we can even fill in the n's at this point, right? So n is 10, right? Because it's always a plus b to the n. Okay, so our a is 3x, our n is 10, our b is 2. So we're going 10, choose k, and 3x to the 10 minus k times 2 to the k. Okay, so we need the coefficient on x to the 7th, right? So that's when 10 minus k is equal to 7, right? Because in that case, 3x to the 10 minus k would be 3x to the 7, and then of course we have 3 to the 7th times x to the 7th, so that would be the term we're after. Okay, so we want to know the value of this, in particular the coefficient of that, without the variable part, when k is equal to what? Well, you solve this equation over here in the box for k, and you should get 3, right? So we're going to let k equal 3 in that equation in the box. We don't want the summation part, just the part in the box. The part in the blue box in particular, so I put it in blue. Okay, so letting k equal 3 into that thing, we have 10 choose 3, then 3x to the 7th, and then 2 to the 3, and then we just evaluate that thing. So 10 choose 3 is 120, times 3 to the 7th times x to the 7th, but I'll push that to the back, times 2 cubed. Okay, and then we want the coefficient, right? So when they say give me the coefficient, they mean everything in front of the variable. Okay, the variable part of the factor, the variable factor part. Okay, so then this will equal, then that implies the coefficient is 20.99520, and that's the answer they want. Okay, they don't want the x to the 7th. Oh, let's see what else they have. So stuff like number 17, I suppose. They give you the binomial version. They want you to rewrite it as a binomial. Okay, so they give you the summation version. They want you to rewrite it as a binomial raised to some power. Okay. So they give you this expression, and they want you to rewrite it as, blank plus blank to the blank. And you just have to kind of figure out what goes in the blank. So the standard form, you may have to remind yourself, they're just using different letters, but they're just dummy variables. So it's going from k equals 0 to n of n choose k, and then we have a to the n minus k, and then b to the k. So you want to kind of align this expression to this expression here in the box. Okay, so it's kind of clear that m is the n part, that I is the k. That must mean a is p, so you'd kind of come over here and fill in the blank there. But it's not so clear what the heck b is. But if you kind of peel off the q to the 4th, you'll have your answer. Okay, it's just q to the 4th, and then raised to the power of m. Okay, so it's just a matter of fooling with the exponent, right? So you can rewrite the original sum as I equals 0 to m of m choose I times p to the m minus I times q to the 4th raised to the I. Okay, and now it's definitely in the form above it. So our b here is the q to the fourth here. And you could rewrite q to the fourth I, q to the 4i, as q to the fourth raised to the ith power. That's just the rules of exponents. Okay. Let's see one more like that. So number 19. Number 19 here, we have the sum from k equals 0 to n of n choose k. We have 5 to the 2n minus 2k, and then 2 to the 2k. And we kind of want to do the same thing that we did last time. So rewrite it so the a and b are easy to identify. Okay? And use rules of exponents. So I can rewrite 5 to the 2n minus 2k by factoring out a 2. Okay, and then we'd have n minus k, like that. And then we could rewrite 2 to the 2k as 2 squared to the k. And then we could rewrite that as a sum from k equals 0 to n of n choose k of 5 squared. So 25 raised to the n minus k, and then 2 squared, or 4, raised to the k. All right. So recall then the original form for our sorry, one second. The original form for the summation part of the binomial theorem is the sum from k equals 0 to n of n choose k times a to the n minus k times b to the k. Hopefully it becomes clear what your a and b is, right? So your a is 5 squared and your b is 2 squared, right? And then we're raising this thing to the nth power, whatever that is. So at the end of the day, it's going to be 25 plus 4 to the n, which of course is 29 to the n. Okay. So they'll have you play around with that sort of thing. I don't think there's any of the combinatorial proofs in there. It's just mainly all this mechanical stuff to get you used to the notation. Later on, if you take a class, again, if you start taking like advanced calculus, or maybe if you're doing some sort of a approximations of functions, approximations of continuous functions with polynomials, they have Bernstein polynomials, which are kind of built off of, it seems like they're built off of these binomial formulas. And what you're able to do is basically approximate any continuous function with a polynomial. I think that's Weierstrass's theorem. And then you could build these polynomials using the Bernstein polynomials, which look an awful lot like these binomial formulas. So you'll get some experience playing around with these guys here, and then hopefully if you see it in the future, it won't be too much of a shock. Okay, so get that homework done, and next time we'll start into graph theory. The next test is just over a lot of probability and a little bit of functions, 7172, right? Okay, so that one will be a time test on WebAssign with 2 submissions. Okay, okie dokie then. I'll see you next time.